Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 31, The Planet Venus. We're going to continue our tour of the planets of our solar system, and in this lecture, let's visit the planet Venus. So again, just some basic facts about Venus so that you can carry these numbers as we go through the rest of the lecture. Venus is about 0.72 astronomical units from the Sun. So it's about 3/4 the distance from the Sun that we are. Its orbital period is a little less than 225 days. So a year on Venus is 225 days. Its orbit is inclined by about 3.4 degrees with respect to the ecliptic. That's the Earth's orbit around the Sun. Its orbital eccentricity is very low. Venus has an almost perfectly circular orbit. Its orbital eccentricity is 0.007. Its diameter is 95% the diameter of the Earth, 12,104 kilometers. So Venus is almost the same size as our planet. Its mass is about 82% the mass of the Earth, so it's almost the same mass as Earth. Its density is similar to the density of the Earth, 5.24 grams per cubic centimeter. And its rotation period, how long it takes to spin on its axis, is 243 days. You'll notice that a day on Venus is longer than a year on Venus. The rotation period is 243 days compared to the period of revolution of 224 days. It's also worth knowing that Venus spins backwards. Of all the planets in the solar system, Venus is the only one whose rotation is retrograde. So that is the planet Venus. We saw earlier when we were talking about Galileo's observations of Venus that Venus goes through phases. So here's an example of Venus going all the way through the half phase down to the waning crescent phase. This was that series of photographs I showed you earlier in the semester, taken by an amateur astronomer in 2002 of Venus going from the gibbous phase all the way through the waning crescent. And then just to show you what the symmetric side looks like, I flipped it over on the other side. So here's the waxing crescent to the half phase to the waxing gibbous. Of course, full is missing because Venus is on the far side of the Sun, and the new Venus is missing because it's just too close to the Sun in the sky to see. From Earth, we can't see anything on the surface of Venus, not because it's so small and far away, but because it's completely enshrouded in clouds. The surface of Venus is completely covered by a thick cloud layer, and those clouds never break. They never allow us to see the surface of Venus. Now, these clouds are composed of droplets of sulfuric acid, and they're typically about 30 to 70 kilometers above the surface. That's sort of 18 to 40 miles above the surface. And by comparison, clouds on Earth are rarely more than 10 miles or about 16 kilometers above the surface. So these clouds are much, much higher up in the atmosphere on Venus. And of course, that has to do in part with the very high temperature on Venus. We'll see that in a second. But of course, for something to condense, for it to get cold enough for condensation, you have to get higher up. This particular photograph was taken by the Mariner 10 spacecraft on its way to Mercury. All right. The atmosphere on Venus is primarily carbon dioxide with an atmospheric pressure that's typically about 90 times our atmospheric pressure on Earth. We saw in the lecture on atmospheres that this is equivalent to about 1,000 meters below the surface of the Earth's ocean, and that's deeper than even nuclear submarines can travel. And if we took a nuclear submarine to the surface of Venus, the atmospheric pressure on Venus would crush the submarine. So the Earth's atmosphere, our atmosphere, is only about 0.03% carbon dioxide. And that's because most of the carbon dioxide is dissolved, in the past, dissolved in the oceans and then was turned into carbonate rocks. And so most of that carbon dioxide today is trapped in sedimentary carbonate rocks. If we were to take all the carbon dioxide from the Earth's oceans and we were to take all the rocks and convert them back into carbon dioxide, our atmosphere would be as thick as Venus's atmosphere. Now, having a thick atmosphere like this means that you can trap a lot of heat. Carbon dioxide is an excellent greenhouse gas. You've got a tremendous atmosphere that is much, much denser and much thicker than the Earth's atmosphere, and it is made of a very good greenhouse gas. And so that means that due to the greenhouse effect, the temperature on Venus is about 740 Kelvin. That's 870 Fahrenheit, and that is hotter than the surface of Mercury. So even though Venus is almost twice the distance from the sun that Mercury is, and by getting twice as far away, that means the sunlight is 4 times dimmer at Venus than it is at Mercury, even with that dimming, because of the greenhouse effect, Venus is the hottest planet in the solar system. And that heat has baked things like sulfur and chlorine and fluorine out of the rocks, because those tend to be very volatile elements that are baked out at low temperatures. And that's what has resulted in the acidic clouds that we find encircling the planet. There is evidence that Venus had once had significant water on the surface. And we get this from studying an isotope of hydrogen called deuterium. Water, of course, is composed of 2 hydrogen atoms and an oxygen atom, H2O. But in the water here on Earth, not all water molecules contain pure hydrogen, that is, hydrogen that has an atomic mass of 1. Some hydrogen in atoms on Earth is made of an isotope of hydrogen called deuterium, which consists of 1 proton and 1 neutron and has an atomic mass of 2. Now, when hydrogen evaporates off of a planet, and hydrogen, you'll remember, is lost from the Earth's atmosphere because we are both too hot and our gravity is too weak to hold on to hydrogen, deuterium is lost more slowly because it is much heavier. It is twice as heavy as a regular hydrogen atom. And what that means, because it's much heavier, is it's moving slower and it's harder to lose. On Venus, you'll have the same thing. Venus once probably had a liquid water ocean, and the evidence for that is that deuterium on Venus, this heavy isotope of hydrogen, is about 150 times more abundant on Venus than it is on Earth. And that may mean that the oceans on Venus evaporated long ago. The water molecules were split apart into their hydrogen and oxygen atoms, and those hydrogen atoms were lost to space. The deuterium, however, gets preferentially left behind because it's heavier and moving slower. So today, when we look at the amount of deuterium, we see that it's much more abundant there than it should be, and that might be because of the loss of these oceans. Based on the amount of deuterium that is left in Venus's atmosphere, we estimate that it might have had enough water on the surface to make a global ocean that was 25 meters, or about 75 feet deep. By comparison, the Earth has enough water on its surface to make an ocean 3,000 meters deep. So Venus has had significantly less water than the Earth does. Well, if we would like to look at the surface of Venus, we have to be able to see down below those clouds, and we can do that using radar. We can use, as we saw with Mercury, giant radio telescopes here on Earth, such as Arecibo, and Arecibo has bounced radar waves off the surface of Venus to map the surface of Venus. We'll see another way that we can use radar waves to map the surface of Venus in a little while, towards the end of this lecture. But we know what the surface of Venus looks like because we've been able to use radar to map the surface. And this is what the surface of Venus looks like. And in fact, in some ways, it's surprisingly Earth-like. And it's Earth-like in that there are very high areas that you could think of like continents, and then low-lying areas. Now, of course, on Earth, the low-lying areas are filled with water. On Venus, it is much, much, much too hot for liquid water to exist. So don't think about these blue areas as containing water, but they are very low-lying regions. Here is another example, another map. This one's a little bit higher resolution, but it doesn't have the names on it. Since Venus was a goddess, all the names on the surface of Venus are typically, the features on Venus, with one exception, are given female names. The one exception to that is Maxwell Montes. It's named for James Clerk Maxwell, the physicist who first figured out electromagnetic radiation. And Maxwell Montes was discovered using radar, using radio waves, and so it was named in his honor. After that was done, it was then decided that everything on the surface of Venus would be named after women. And that is where many of the names come from. So this is the topography of the surface of Venus, again determined by radar. The one thing that we don't see on the surface of Venus is we don't see things like the Mid-Atlantic Ridge. We don't see any evidence for plate tectonics on Venus. So there's no evidence of plate tectonics on the planet Venus. However, just looking at this image, we can tell one really interesting thing. We can actually compare the surface of Venus to the surface of Mercury and determine which one is older. So, just like we did with the moon, I want you to look at the surface of Mercury on the left and Venus on the right. And I want you to tell me how the age of the surface of Venus compares to the age of the surface of Mercury. Is Venus's surface much younger? Is Venus's surface much older? Or are they about the same age? Go ahead and take 10 seconds and answer this question. All right, what did you come up with this one? Well, you'll remember that we determine the age of a surface by counting the number of craters per square mile per square kilometer. And you can see that the surface of Mercury is covered in lots and lots of craters. And that indicates that the surface of Mercury is old and ancient like the surface of our moon. But just looking at the image of Venus, it's not clear that you see any impact craters. There are, it turns out, a few impact craters on the surface of Venus. But as we look at this planet as a whole, we can see hardly any impact craters at all on the surface. So that means the surface of Venus is much younger than the surface of Mercury. But now I want you to answer this learning catalytics question. How does the age of the surface of Venus compare to the age of the surface of the Earth? So go ahead and take a few seconds to answer this question. How does Venus's surface compare to the Earth's surface? Is it much younger or about the same age as the Earth's surface, or is it much older? All right, so what did you think on this one? Well, I would have to argue, given the lack of impact craters on the surface of Venus, the fact that there are so few, and given the lack of craters on the surface of the Earth, that the surface of Venus and the surface of the Earth are about the same age. So I would argue that the answer to this one is A. Venus's surface is about the same age as the surface of the Earth. Could be younger, could be older, but it's about the same age. There is, in fact, evidence on Venus from crater counting that many regions on the surface of Venus are actually quite young. That hundreds of millions of years ago, there may have been massive, massive lava flows on the surface of Venus. Now, we haven't seen that with our radar observations today. If there are any lavas flowing on the surface of Venus today, they're limited in extent. But it looks like there may have been an a planet-wide ocean of flowing lava hundreds of millions of years ago on the surface of Venus. And much of the surface of the Earth is hundreds of millions of years old. And so that would put the two of them at about the same age. Where does this lava come from? Well, Venus has volcanoes. So this is the volcano Sapis Mons. And so we'll learn more about the volcanoes in a minute, but I just wanted to mention that right now, that this is a volcano on the surface of Venus. You'll notice that this little arrow here, that's 100 kilometers, which is 60 miles across. So this is a monstrous volcano right here. So this volcano is probably, I would argue, 600 kilometers in diameter from side to side. You can see the lava flows flowing out onto the surface out here, some of them flowing quite extensively, quite far from the caldera of the volcano, which we can see right in the center. Now, a number of spacecraft have landed on the surface of Venus. Most of those that have landed on the surface of Venus are Russian vehicles, and they're part of the Venera series of vehicles. The United States did have a Pioneer probe that parachuted down through the atmosphere of Venus, and it wasn't designed to land on the surface. It did not have any landing legs or anything, but it turns out as they parachuted down through the atmosphere, they did in fact hit the surface and survive on the surface for a short period of time. But the Russians are the only ones that have landed true landers on the surface with cameras to photograph the surface. That was done from 1961 to 1984, but they weren't actually successful with doing this until Venera 7 on December 15th, 1970. It was not only the first vehicle to land on Venus, but it was the first soft landing on another planet by any country. And altogether, the former Soviet Union has landed 10 spacecraft on Venus. So these spacecraft consisted of two parts. There was a flyby spacecraft, and then there was the lander that landed down on the surface. Now, the thing about these landers are the surface of Venus is so hot that they can't survive for very long. So these are not landers that survived on the surface of Venus for days or months or years even. These landers typically lasted a couple hours down on the surface, typically about 2 hours at most. So that's how long the landers last. Venera 13 was one of the more successful missions. It was launched in October of 1981, took 4 months to cruise to get to Venus. It arrived in March of 1982. It used a parachute to get down from 63 kilometers to 47 kilometers above the surface. And after that, the atmosphere on Venus was so thick that it was able to use simple air braking to slow itself down to get down to the surface. You can see that it has this large flat bottom on it. And the atmosphere was so thick that the wind resistance on that large bottom as it was coming in provided the braking that was needed to get down to the surface. And then the lander survived on the surface for just a little bit longer than 2 hours down on the surface. It was able to measure the temperature at the surface where it landed. It was 855 degrees Fahrenheit, or about 730 Kelvin. And the atmospheric pressure, as expected, was 89 times the Earth's atmospheric pressure. That means that this spacecraft had to be specially designed to survive those intense pressures. Remember, the pressures are so great that they would crush a U.S. nuclear submarine. So this container here, this spacecraft, looks like it's very bulky because it is. It's actually built so that it's much stronger than a U.S. nuclear submarine, so that it could withstand those tremendous pressures on the surface. And there was a camera mounted on the side that, as I mentioned earlier in a previous lecture, sort of scanned up in one direction and then scanned up in the other direction. And so it took these sort of odd photographs where it's staring at the foot of the vehicle, and then it scans up and looks in this direction, and it scans up and looks in that direction right there. And this is what the surface of Venus would look like under Earth lighting conditions. But you might remember that the atmosphere is so thick that all the blue light gets scattered away and only the red light makes it down to the surface. And this is what it would look like if you were standing on the surface of Venus. The surface would be a dark, deep red color. Dark because not as much light makes it down to the surface as we get here on the surface of the Earth, and deep red because all the blue light is scattered away. Now, these images are distorted by the camera sort of rotating up and rotating down. So someone has taken these and projected them, used a computer to fix the projection. And so this is what they look like when they're unprojected. So this is what the Venera spacecraft saw on the surface of Venus. This particular image right here is actually this image right here. You can see this rock right here. That rock is that one right there. And then if you look at this thing off in the distance that has a little hook hanging down right there, that's that little hook right there, that flat rock right there. So this image is actually that one that I just showed you a second ago. But now it's rectified so that this is what it would look like if we were standing on the surface, as opposed to that sort of crazy distortion. I mentioned earlier that Venus has volcanoes. This is Sapis Mons, one of those volcanoes. Sapis Mons is sort of right here in the foreground. Other volcanoes off in the distance. That is Mont Mons, another volcano on the surface of Venus. And it raises the question, what kind of volcanoes does Venus have? Does Venus have composite or stratovolcanoes, or does it have shield volcanoes? Now, you might remember the difference between these. When you have plate tectonics here on Earth, when an oceanic plate gets pushed underneath a continental plate, as that oceanic plate pushes underneath, the materials in that plate that have low melting points will melt, and they will work their way up to the surface. And as they work their way up to the surface, they will form chains of volcanoes. And these are the stratovolcanoes, or the composite volcanoes, as they're called. That's what we have here on the west coast of the United States. We have Mount Rainier, we have Mount St. Helens, we have Mount Hood, for example, Mount Shasta down here. These are all volcanoes where the Pacific plate, or a plate under the Pacific Ocean, is diving underneath the North American plate, and as it melts, that molten material comes up and forms these volcanoes, these composite or steep-sided stratovolcanoes. So there's Mount Rainier, for example. Before its explosion, this is Mount St. Helens in the foreground and Mount Rainier in the background. And you'll remember the difference between these stratovolcanoes and shield volcanoes is that shield volcanoes are made up of very runny lava. And that runny lava doesn't build up into nice steep sides like that. It sort of flows out. And that's why the shield volcanoes such as Mauna Kea and Mauna Loa in Hawaii are very broad and very flat. They're not peaked like that at all. So that is what shield volcanoes look like. And that's, again, because the lava, remember, this is basaltic lava, which is lava that is rich in iron. And that iron-rich lava flows very easily across surfaces, draping itself across the surface. What happens in one of these shield volcanoes is you have a magma chamber deep down underneath, and the lava flows across the surface, and then it solidifies, and then another flow on top of that, and it solidifies, and another flow, and another flow, and another flow, and another flow. When you look at Mauna Kea and Mauna Loa, they are not from giant monolithic eruptions where one giant eruption let out all that lava. In fact, they're made up of thousands upon thousands of individual lava flows, where the lava flows for a while, freezes, and then flows again and freezes and flows again and freezes, and the volcano builds up layer by layer by layer like that. So that's what a shield volcano is. So the question is, what kinds of volcanoes do they have on Venus? Are the volcanoes on Venus shield volcanoes, or are they composite volcanoes? Well, when you look at the pictures of these volcanoes, you might think to yourself, well, the volcanoes look like composite volcanoes because they're very steep-sided. But you'll notice over here that the vertical scale is exaggerated by a factor of 15. And they do that because they look a lot more interesting when they have these steep sides to them. If we actually showed them as they really are, they look like little rolling hills. They look much more like shield volcanoes. All right. So if we make a computer model, an image of a mountain, and this is what the mountain looks like, we can exaggerate the vertical profile to make it look more exaggerated. And that's what's been done in a lot of those images of the volcanoes on Venus. Now, you might remember here on Earth that, especially in the Hawaiian island chain, that the Earth's crust is moving along, so that as the hot spot works on building a volcano, the plate motion pulls the volcano away from the hot spot. The hot spot has to start over with a new volcano, and that original volcano that gets pulled to the side eventually erodes away over time. The Hawaiian Islands are an example of this. Loihi is the new volcanic location where there's a new volcano being born deep under the ocean. The island of Hawaii is the youngest of the Hawaiian Islands. And as we get further to the west, the islands get older and older. So on Kauai, the last eruption was 5 million years ago. On Oahu, it was about 3 million years ago. Maui had eruptions as recently as 1 million years ago. And of course, there are still active volcanoes on the southeast edge of the big island of Hawaii right now. So that's the island of Hawaii. So the mountains on Venus are actually shield volcanoes. They are not the steep-sided, and in fact, even this one is grossly exaggerated, right? These are supposed to be shield volcanoes, but they've grossly exaggerated the height compared to the width on these. They should look much more like that, but that's not terribly interesting to look at. So sometimes on the figure, they exaggerate them. So the Venera spacecraft land on the surface of Venus. The surface of Venus is lots of volcanic flows that came from these shield volcanoes. So what kind of rocks did the Venera spacecraft find at their landing site? Did the Venera spacecraft find rhyolite, which are lighter colored rocks, lighter colored lava that we get from composite stratovolcanoes? Or is it the basalt, the dark colored lavas that we get from shield volcanoes? Or were they sedimentary rocks deposited in a shallow sea? What do you think the Venera spacecraft found when it landed on the surface of Venus? Go ahead and take a few seconds to answer this one. So what do you think they found? Well, the volcanoes on Venus are shield volcanoes. And that type of lava is basaltic lava. And so, in fact, the landers had scientific instruments to measure the composition of the rocks that they landed on. And the rocks that they landed on were basaltic lava flows like this. In fact, a tremendous fraction of the surface of Venus is covered in basaltic lava flows. Well, let's talk a little bit more about mapping the surface of Venus. The mission that has done the most to map the surface of Venus is called the Magellan mission to Venus. Magellan was launched on the Space Shuttle Atlantis in May of 1989. And it's a really interesting mission because the spacecraft was made up of actually a lot of spare parts. They took spare parts from the Voyager mission, the Galileo mission to Jupiter, the Ulysses mission to study the sun, the Mariner 9 mission. They put all these parts together. They put together new parts that they needed to build for it. And they built a spacecraft whose job was to go to Venus and use its giant radar dish here to send radio waves through the clouds on Venus and map the surface of Venus. And we call this kind of radar mapping synthetic aperture radar. Radar because we're bouncing radio waves off the surface. Radio waves, we know how fast they travel at the speed of light. So as the radio waves go down and they bounce off the surface and come back, how long it takes them to go down and come back tells us how far away the surface is. But different pieces of the surface are different distances. Some of the radar waves bounce back earlier for the stuff that's close to us. Some of the radar waves bounce back later for the stuff that's farther away. So that is one of the ways we can use this synthetic aperture radar to map the surface. All right. It was launched on the Space Shuttle Atlantis, I said, is in 1989. It got to Venus, so there it is being released from the cargo bay of the Space Shuttle. It flew to Venus, and it used its giant dish to do synthetic aperture radar. So it had another small radio horn on the side, so you can actually see it right there. So this little horn right here, that's a radio transmitter that sent radio waves straight down to the surface and straight back up. And that was able to tell the spacecraft its altitude. But more importantly, because we knew the orbit of the spacecraft quite well, it could tell us the surface topography. So that could tell us the altitudes of the surface. And then the synthetic aperture radar itself looked not straight below the spacecraft, but off to the side. And as it looked to the side, these lines here mark lines of constant range. That is, radar waves would bounce off the surface and come back. Because these are closer to the spacecraft, they would come back first. Because these are farther away, they would come back second. In addition, there is a Doppler effect. As the spacecraft is orbiting across Venus, parts of the surface are coming towards the spacecraft, parts of the surface are moving away from the spacecraft, and the parts that are coming towards the spacecraft over here have a different Doppler shift than the stuff moving away from the spacecraft over there. So the spacecraft was able to bounce the radar waves off the surface, and from using the time of return, when the radar waves returned, and from using the Doppler shift of the radar waves, it was able to figure out where in this footprint the radar waves came from. And that allowed it to map the surface very accurately. And so this was the orbit of the spacecraft right here. It was in an elliptical orbit. So when it was close to Venus, it used its radar to map the surface. And then as it pulled away from Venus in its elliptical orbit, it would reorient itself, point its giant antenna back to Earth, and it would play back all the data to Earth. And then it would turn itself, and it would go back to mapping, and then turn itself, play back to Earth, turn, map, turn, play back to Earth, and just do this over and over again. And it is the Magellan mission to Venus that gave us these absolutely amazing images of the volcanoes on Venus, like Mont Mons and Sapis Mons, and this one of Sapis Mons again. So these are the volcanoes on Venus, and these fantastic maps of these volcanoes came from the Magellan mission to Venus. Well, that is all I'm going to say about Venus. So our next episode, our next lecture, will be on Mars. We will study Mars. It'll be a bit longer of a lecture because there's a lot to say about Mars, and we have a lot of missions at Mars. And so join me in my next lecture when we talk about the planet Mars.